think it's working. Yeah, all right, cool. Hello, everyone. Sorry about the technical difficulties. Bit of a mix-up on our end, but it seems to be sorted out, so that's good news. Welcome. We're going to wait a little bit for the view count to kind of stabilize as people trickle in, and then we'll get started shortly. All right, we're still starting to see people coming in now, so we'll give it another minute or so. All right, I figured let's get started. Hi, everyone. Welcome to Universe at Home, and in fact, the last Universe at Home of this season. Please stay tuned. We don't really know what the situation for the summer is going to be yet, but there is a good chance that we'll have a couple more of these streams coming for you over the summer. We'll try to be in touch as that gets sorted out. Everything is very much in flux. But without further ado, I'm Alexander Criswell, and I'll let my co-hosts introduce themselves.
Hello everyone. So I'm Babhov, and I'll be starting the like I'll be giving a brief overview of whatever I want to say, and then Alexander will take over for the activity. So let's start then. Okay. So as you guys already know, the topic for today's presentation sort of is going to be on the constituents of this universe. By this universe, I mean our universe, of course. We don't know of any other universe as of now. Um, Again, Anne is the person who is looking into the tech handling of things. So she would be relaying your questions to me when the time for that comes. So let's start. Okay, so I would like to start with a question. Just imagine everything that comes to your mind when you think of what constitutes the universe. You can think of something around you, maybe start with your room, go to something that you can conceivably ever see from a satellite image, let's say an Earth or something like that. You zoom out further, you go to the solar system, and so on and so forth. You go all the way to the edge of the observable universe. Whenever you imagine anything like that, starting from something as local as the Earth to the edge of the observable universe, you always think of light coming from objects, right? Like you observe the sun because of the light coming from it, you observe a galaxy because of the light coming from it, and so on and so forth. you know uh, but then again, what if I tell you that everything that you just saw in the previous image, even the light coming from the observable universe, from the entire box of the observable universe, constitutes just 5% of the mass and energy of the universe. I mean, it's sort of surprising, right? Well, um, that's what we have found out after years of exploration, and we are now pretty much sure that that's about the right number, and we can tell it pretty confidently that everything that either emits or absorbs light consists only about, it's even less than 5% of the total mass and energy of the universe. So what is the rest of the 95% consisted of? So the answer to that is that there is a huge chunk of energy consisted in something that we call as dark energy, and then there is a dominant portion hidden in something called as dark matter. So what does this 4.6% of energy budget or mass and energy consist of? Like, this consists of every atom, subatomic particle in any form that you can think of. Okay, so right now we'll see that around 95% of the mass energy budget goes into this, something like this, which we call as dark matter and dark energy. So it's pretty common for people to think that these might be somehow related because the naming scheme is pretty similar. This is dark and stuff like that. But dark is just like, physicists are dull, so they just don't want to put in any effort to, name something, like give a serious thought into naming something. Dark just means that we don't know much about these things, and our ignorance is captured in the word dark. Other than that, these things are not related at all. And also, it may mean that it doesn't interact with electromagnetic radiation or light, and hence the opposite of that, which is dark. All right, then. So we'll start with dark matter. So, how do we even detect something that you can't see? Okay, so this might be the first question that comes to your mind. The answer is simple but quite brilliant. So dark matter doesn't emit any light, but it does interact gravitationally, and that's how we detect it. So it has got effect on the, like, it has got effect on the stars that orbit the galaxy or the light that travels, and we are going to discuss a few cases of that. Okay, so these like galaxies are the systems where dark matter was discovered for the first time by, like, the first detection was by Vera Rubin. And so what is this thing that we say that that, like, what is this thing that concludes the presence of dark matter in the galaxies? So if you see out here, there's a galaxy out here. So the light ends somewhere around here, right? So let's ignore the portion before this. After this portion, the velocity, this is a velocity versus distance graph. The velocity should fall. Okay, from Newtonian gravity, you can, like, it's a two-line derivation where you can show that the velocity squared goes over as 1 over r, and so it should fall off after the light ends at the border of the galaxy. After the border of the galaxy, it should fall off. But what was observed was that it doesn't. Instead, it keeps on rising. So that puzzled her. Like, what might be the reason for this? Is there something that we are not accounting for? Well, the easiest explanation right now is that you have something that you can't see, but which has got mass, and that's what is causing the velocity to keep on rising, like it was doing in this portion. Like, it was keeping on rising because there was mass, so it keeps on rising because there is more mass that you can't see. So that's when it became clear, like, that's how the presence of dark matter was hypothesized. And this is a pretty famous way of detecting dark matter in galaxies, and this is called, you just plot the rotation curve, meaning the velocity versus distance, and you find out how much mass is there in the galaxy. So then there is something that we can't see, but it does interact gravitationally, hence the name. it's called dark matter because it has got mass and doesn't interact with light or emit light or anything like that. So in fact, most of the galaxies have masses much higher than the mass that emits the light. Like most of the galaxies have mass around 10 times higher than mass of around 10 times the dark matter, 10 times the mass which emits light in dark matter. So then is this the only system where we observe dark matter? I mean, if it is present, it should be present like in multiple scales and not just covering the galaxy or something like that. So the first thing to note is that this effect is not peculiar to one galaxy and has been seen in many galaxies. And it's now a common thing that, dark matter halos are present where the sort of where the galaxy resides. The galaxy resides inside a dark matter halo. But the effect of dark matter is more dominant in more massive systems like clusters of galaxies and so on. So what happens is that in case of clusters of galaxies, these are huge systems. Okay, these contain something like order of 1,000 galaxies or something like that. So these are heavy enough to curve the space time, and these produce effects similar to how a glass lens sort of bends light rays. You know, and this sorry for that. And this sorry, pardon me. And this effect is called gravitational lensing. We can measure the mass of the lensing system by the amount of bending that the light uh, amount of bending that it causes to the background light. So what is lensing? So right now, if you see a massive object present between a background and you can observe that the light rays bend around that massive object, and you can sort of see an extended image of the object, multiple images of the same object because light bends around all the directions. So these are some pretty pictures of, these are called Einstein rings. And these are the images of the lensed background galaxy that causes these sort of distortions. So it is, people have been able to calculate the mass of the systems that is needed in order to form these distortions. And when they find out the mass of these systems, they find that the mass that is required to form this light is nowhere close to the mass that is required to form these distortions. What that means is that actually the mass present in clusters is around 20 to 50 times the mass calculated from visible matter. So then let's come to this. This is a real famous image of bullet cluster. So this is another way of probing the presence of dark matter. So what is happening out here is that two subclusters are interacting. So the red portion, red region is sort of what is the visible matter. And then what you do is that you apply the similar thing to the background, to these subsystems. You find some lensing systems around that, and you find the center of mass of these systems. So you find that the center of mass actually resides in these two positions in the invisible region. So you aren't seeing anything out here, but this is sort of the mass distribution that has been given by the lensing. So that's that's surprising, right? Because the visible matter is somewhat like is hugely displaced from the center of mass. And what's the explanation for that? So the simple explanation that people like, it's not a simple explanation, but what has happened out here is that as the galaxies subclusters of galaxies have combined, merged together, the atoms and everything have sort of interacted with each other. Like the gas in one galaxy has interacted with another, but the dark matter just passed through because it doesn't interact in the same way that normal gas does. So the 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 visible matter remained, but the dark matter halo just passed through into this, no, onto this direction, and similarly onto this direction. So this is somewhat something that we call as cross section. This is just that, if you collide two particles, what is the probability of their interaction? So the cross section of dark matter is very low. That is, it doesn't interact easily with anything. And that's why it is sort of very difficult to detect directly. Okay. So galaxies, clusters, everything reside inside dark matter halos. We have seen enough evidence of that, and we have more evidence of that as well. So what we want to say here is that we don't know the nature of dark matter. There have been many theories, but there is no conclusive experimental evidence. And this is a very, very active research area. And again, so we have got experiments like CDMS, which is cold dark matter search experiment, which is, which has got strong contributions from researchers from UMN. It is actually inside Sudan mines in Minnesota. So that's it about dark matter. And now we go on to dark energy. So we now know about around 25% of the energy budget, which we didn't know earlier. Now let's come to the dominant fraction of energy mass of the universe. So what do we know about what is our current understanding of our universe, so as to say? So it all started with a big bang, and then the universe expanded. And let's not concentrate on things around here. The first stars formed, galaxies formed, planets formed. Right now, this is the epoch that we are at right now. And let's just focus on this terminology called expansion. So you must have heard it that we are in an expanding universe. So what does an expanding universe even mean? But then again, how are we so sure that the universe is expanding? And if everything is expanding from away from us, then does it mean that we are at the center of the universe? Because that's what we assume when we hear that everything is expanding away from us, right? So let's consider this simple thought experiment, because it's pretty well motivated. So consider a grid of galaxies. So we are in a homogeneous universe, homogeneous and isotropic universe. What that means is that, like, on large enough scales, it is pretty uniformly distributed. Matter is pretty uniformly distributed on large enough scales. So let's consider at an earlier time, these were the positions, and after a certain instant of time, the background sort of expanded. That's what actually expansion means, is that the background expands. So what it means is that, let's say the distance between the galaxies, the pair of galaxies out here, was 1 unit, then it goes to 1.1 unit. Let's assume that that's the case. But again, if you're looking at the sky right now, you only see the positions of the galaxies, right? Either this one or this one. You can't say whether it has expanded from a previous time to this time. But that's where our perspective comes into play. So if we fix a point, let's say we are sitting on this yellow galaxy out here. So if we fix this point, because we are not moving with time, what will happen is that if we superimpose both of these images together, because we are static, what we'll see is that there will be a shift in the position of the other galaxies. So by that principle, we should be able to observe the change in position because we are stationary. So perspective becomes important out here. But then again, we know that the universe is expanding because the positions of the galaxies have changed. They are going away from us. But then again, are we at the center just because the other galaxies are moving away from us? The answer is no, because no matter where you take it, like no matter if you take the yellow galaxy to be your home galaxy or the red one, always things will be moving away from us. So let us relate to a more day-to-day life example out here. So if you have got, let's say you are baking some bread, and you have some raisins in it. So in the dough itself, the raisins are close by, right? But as the bread gets baked, it sort of expands, and each raisin is sort of going away from each other, but no particular raisin is at the center. So that's sort of the principle that we are getting into here. So the take home point out here is that farther galaxies should be moving away from us faster in an expanding universe. At least that's what we see out here. And every galaxy sees like every other galaxy moving away from it. So no one is basically at the center. Basically, no one requires to be at the center to see every other galaxy moving away from it. Okay, then. So even if we know that we are in an expanding universe, like how do we know that, first of all, and how do we measure that? So the way to measure it is something that you use sort of without even thinking. So if you're standing by the, on the side of a road, and let's say you are on a mobile or something, you need not look at the road to know whether a car is approaching you or it is going away from you, because because of something called Doppler shift. What happens is that if the car is approaching you, the pitch sort of starts rising, and as the car departs away from you, it sort of the pitch starts coming down again. So that's the same thing that is happening out here. As the galaxy, if a galaxy is approaching us, it will get blue shifted, which means that the pitch of the wavelength will get shorter and the frequency will increase, frequency of light will increase, and that is what we call blue shift. And if a galaxy is going away from us, it will be red shifted. So in an expanding universe, galaxies far away from us should always be red shifted. And that's what Hubble found out, and we call this as Hubble-Lemaitre's law. So what he found out was that galaxies which are far away from us, so parsec is a unit of distance. So galaxies which are far away from us are moving away at a way faster velocity than the galaxies that are near to us. Okay. So, and that's what we expect in an expanding universe. So we know that we are in an expanding universe right now. So then how do we detect dark energy? So the way to detect dark energies is to detect galaxies that are far away from us, meaning like that are so far away, like along this line. So this is a very close space, like 2 megaparsec is a close distance, meaning not really close, but in terms of cosmological distances, this is a close distance. So we want to find objects which are at a much higher distance so that we can find sort of traces of dark energy in it that has been found out. But there is there is still a quest to go on and observe more objects which are at even farther distances. So DES is one such survey, which is currently observing around 400 million astronomical objects, which is going to the data set is going to be huge, and then we can measure sort of dark energy and everything, those things more accurately. So there is another way to measure it, which is called by measuring the something we call as the power spectral density of the cosmic microwave background, which people have used and found out the energy density residing in dark matter as well, and pretty accurately to that. So we'll end the talk part of this this universe at home right now. So the key takeaways that I want you to remember is that only a very small fraction, that is even less than 5% of the mass and energy, is in terms of normal matter, meaning every element that you know, every atom that you know of, subatomic particles, everything has got only less than even 5% of the mass and energy of the universe. A dominant fraction of mass and energy is in form of dark energy, which is responsible for the accelerated expansion of the universe. Excuse me. And a considerable fraction, around 25% of the energy is in form of dark matter, which interacts gravitationally and doesn't emit or absorb any light, so as to say. So these are the three main components, and I will take questions now.
Okay, our first question comes to us from somebody named Moorington, who says that so we conclude that dark matter is inert, has no radiation, and does not reflect light from other bodies, or is that too simple of a characterization?
I think that's pretty true. I mean, it doesn't interact with light in any manner, any mannerism possible. But even with that, like, there are many more characteristics to it. So the bullet cluster diagram that we showed earlier just shows that it is way less interactive, even collisionally, meaning it just passes through stuffs, and that's the primary reason why it's hard to detect. But yes, it doesn't interact with light in any manner.
I think that one of the fun theories that I've seen that some folks work with is the idea of an entire dark sector. So an equivalent for photons that would interact with dark matter but not regular matter, and so on, which would mean that dark matter acts sort of like regular matter, but only with other dark components of the universe. So there's a couple different ways that you can look at dark matter, and like we've really established in this talk, we still don't know what it is. So we're trying to figure that out.
I hope that answers this question. So is there any other question?
There are no questions right now in the chat, but yeah, if you have any questions, just ask. There's no such thing as a stupid question. This is a wild topic and we almost know almost nothing about it, so feel free to ask.
Yeah, I figured that while folks think of questions that they would like to ask, I can just carry over to the activity and talk a little bit more about how you can actually help with trying to advance our understanding of dark energy.
I will keep an eye on the chat. If you have a question, I will see it.
That would be fantastic. Thank you, Anne. So I'm going to throw the link to the project into the chat there, and then go ahead and share my screen. And so what I'm showing to you right now is a project on the Zooniverse platform. It's a citizen science project called Dark Energy Explorers. And the idea is that, the astronomers behind this project have these very deep surveys going back to the early times of the universe, when the universe was only 2.3 billion, or 2 to 3 rather, billion years old, as opposed to the 14 some that it is now. And the issue is that they have all of this data. They've done really deep surveys and really wide surveys across the entire sky, which makes classification of the data that they've actually gotten really difficult. There are some folks that are trying to classify these things using processes like machine learning, but another way to handle a problem where you have thousands and thousands, or even hundreds of thousands of samples and pieces of data that do actually need to be classified by a human is to use citizen science. And so the way that you can actually help this project is by contributing to it through the Zooniverse platform, which you can access via the link that I put in the chat. And the basic idea is that they are trying to figure out whether their data is for galaxies that are nearby, or stars in our own galaxy, which is not things that they're interested in, or if this data is from a very, very far away galaxy that will actually allow them to measure how much the light from that galaxy is being stretched by the expansion of the universe, as it travels across almost the entire length of the universe. Because again, we're looking for galaxies that are from when the universe was maybe 2 or 3 billion years old, very young on cosmological terms. And so what we have here is a bit of a complicated diagram, but I'll break it down for you. In the bottom here is the light curve of this galaxy. And the dark line is their model that they're fitting to it. And the first thing that you want to check is to make sure that this curve actually matches up. If it doesn't, then you want to hit the distant galaxy or nothing, because in this case it would be nothing, it would be an error. And then you want to make sure this is the spectra. So they're basically looking at a bunch of different wavelengths of light. And you see these little black dots that are in here, these little overdensities. That's their actual measurement. And they can use that to try to figure out how much expansion the universe has undergone in between that light leaving its original galaxy and arriving at our telescope. And so the way that they sort out between nearby galaxies and distant galaxies is they've got these little Olympics looking rings, and this entire red box is this area of the sky field. And it's very straightforward. Either you see a big blob in this space, in which case that's probably a nearby galaxy or a star, or you don't see much of anything at all, or a very small object that's smaller than one of these circles in this area. So this, we've got the nice light curve, we've got some spectra, I don't see any contaminating objects. That's a distant galaxy. Let's keep going. Now this is perfect. Couldn't ask for a better counterexample, because we still see some spectra, the light curve is still kosher, but boy, that's definitely a big old fuzzy object that is in the middle of our field of view. And so this is probably a nearby galaxy or a star, and we can continue on like this. And this project, basically, you can go in, and it's a very straightforward task that you can do. But what you're doing is you're helping astronomers actually manage to classify this data set and measure the expansion rate of the universe. So I always get a kick out of these citizen science projects. I think they're really fun, and especially when we're all stuck inside, it's a good way to kind of spend some time. Again, you can see there's a big old fuzzy blob in our field of view here, so that's definitely a nearby galaxy. This one's tricky because it might be that we're getting the contribution from this, but it might be that there's a distant galaxy hidden in there. But based on the magnitude of the dark spots in the spectrum, I'm guessing it's also a nearby galaxy. And this one too. So we're getting rid of all of these bits of crap data that are in their data set that they don't want, and getting at things like this where we can actually see that, well, there's nothing that we can see by eye there, which means it's a very small or very faint object, which means it's far away. So we've got a distant galaxy. That's pretty much the idea with this particular Zooniverse project. It's one of the more straightforward ones in my experience, but it's an easy way that you can kill some time and help actual astronomers do some science and understand the expansion of the universe and understand dark energy. Do we have any more questions that have come in, Anne?
Yeah, we have at least one.
Awesome.
Mike asks us, does dark matter orbit the center of galaxy the same as the stars?
I believe so, because I've seen people who work with dark matter simulations, and the only thing that they put in is that you have dark matter particles and you put those in and you just let it evolve gravitationally. So every gravitational effect that is present for normal matter should be present for dark matter as well. And Alexander, do you want to?
Yeah, I think you put it fairly well with that last sentence there. Dark matter interacts gravitationally, which means that just like all of the other bits of luminous matter or regular matter in a galaxy, it will orbit around with everything else in the gravitational field of the galaxy. That being said, something that Bob mentioned during his talk is that galaxies usually have about 10 times the amount of dark matter than they do luminous matter, which means it's more that all of the luminous matter is orbiting in the gravitational field created by the dark matter. And that's something that we call a dark matter halo. Towards the core of the galaxy, it's dominated by the light matter. You have a lot of stars there. In most galaxies, you've got some sort of supermassive or intermediate mass black hole. But once you start getting out into the outer reaches of the galaxy, the dynamics are largely dominated by the dark matter that's hanging out. Are we seeing any other questions coming in now?
I'm not seeing any other questions right now, but there's still time to ask if anybody has anything.
For sure, we'll give it a little bit more. Excellent.
Will we ever have the technology to send a physical probe that far out to investigate or measure dark matter more closely?
Ever's a long time.
Like, that depends on if we know what we're probing for.
Yeah, that's the issue out here is that the cross section, that is the probability of the interaction of a dark matter particle with anything, is extremely low. So dark matter should be actually, in principle, it should be present everywhere. Like, you won't see it dominating the mass at something like scale of a solar system or something like that. It would dominate at larger scales, but it should, like, in theory, pass through the Earth right now as well, because it shouldn't interact, and the probability of interaction would be very small. But in principle, you can create detectors, and that's what experiments like CDMS and those people are doing. So they go deep underground where nothing else can come through. You block out all the cosmic rays, you block out everything else, so that the only dominant particle that can come through is dark matter. And then as it comes through, if it interacts, then it will deposit the energy and you sort of see it. That's how you detect dark matter. But there hasn't been a lot of success. I mean, we have discarded a lot of theories in that way, but again, it's an extremely difficult problem.
One of my favorite fun facts related to this is that at any given time, there is approximately 1 squirrel's worth of dark matter in the general vicinity of the Earth specifically. So that gives you an idea of the density that we're dealing with here, about 1 squirrel per Earth volume. The other thing that I thought that was really neat, I listened to a talk about this a while back, is that one of the ways that you can probe for dark matter is just use the fact that the Earth is orbiting the sun, which means that about half the time the Earth is moving along with the flow of all of the gas and dark matter and everything else that is orbiting around the center of the galaxy along with the solar system. And the other, half the time it's moving against that flow. And so there are folks who are looking for a yearly modulation in the in particle interactions, because as long as you can make sure that that's not caused by anything else, that would be a dark matter signature, because you in theory would have more dark matter flux going through the Earth when you're going against the stream, so to speak, than when you are going with it. So you can use the Earth itself as a probe of sorts. So I guess to really answer your question, we don't have to send a probe very far out because the dark matter's here already. I think we can probably
I'm waiting for the delay to catch up to see if there's another question.
That's what I was about to say as well. So we can give it another minute or two to see if anybody has any burning questions that they want to ask here. Otherwise, we'll probably wrap it up and call it a night pretty soon. While we're waiting, do you folks have any favorite dark matter facts or dark energy facts, for that matter, that we'd like to share?
I mean, my favorite is how many times people have said, well, what if dark matter is this size of black hole? And then we do some experiments and it's not there. It's like, okay, what about this size of black hole? And we do some experiments and it's not that. It's probably not black holes at this point.
People have got really creative with that. I think my favorite way of disproving dark matter is a bunch of tiny black holes was they did a lensing survey looking at like very small bits of gravitational lensing of the sort that would be caused by like, a very small black hole. And they looked out across the entire sky and they computed the statistical chance of never seeing a single microlensing event of the order expected from one of these tiny black holes if they were actually out there was something like 1 in a few billion. So we're pretty sure it's not black holes, which is probably good news for advanced spacefaring civilizations.
Yeah, and modified Newtonian dynamics was suggested as a theory for dark matter. I mean, bullet cluster, the observation of that sort of disproved it at, something like 1 in 10 billions or something like that. But, before that, it was a really strong contender for explaining.
To clarify what modified Newtonian dynamics is just folks theorized that gravity just works differently at very large scales than the typical Newtonian or even the general relativistic formulation of it would predict. And that's why we see this weird behavior in galaxies and clusters at large scales. But like you said, Bob, the bullet cluster kind of, put a bullet in that one.
Yeah. Okay, we have a couple more questions. When was dark matter first discovered? Or I guess theorized is probably a better way to put that. Because we haven't technically discovered it yet.
I mean, empirical observations.
So I guess it was first discovered with Vera Rubin, but I don't remember when that was.
Yeah, Vera Rubin. I was trying to remember her name.
Is it 30s? I think it's...
I want to say it's 30s. It wasn't too long. It's like we found out there were other galaxies, and then we immediately figured out there was something weird going on.
Yes.
Yeah, 1933.
1933. Okay, we got another one from Kevin who says, do you consider that dark energy is a property of space itself and therefore exists everywhere in the universe at a constant level?
I want to chime in before we move on and clarify. It was theorized in 1933, but Vera Rubin actually made the first observations that implied that it was actually a necessary part of the universe in the late 1970s.
Oh, wow, geez. That's a new one.
Yeah. So as for dark energy being the property of the space-time itself, that this is a very dominant theory, like general relativity, which describes the space-time, does consider something called the gravitational constant, which takes the form of dark energy, like which we think is dark energy actually. So, and could you please repeat that question again? Sort of.
Do you consider that energy is a property of space itself and therefore exists everywhere in the universe at a constant level? So I think this question is basically asking, like, does the amount of dark energy vary, or is it, as some people have proposed, an inherent property of space-time itself?
Yeah, so that's what the cosmological constant is. By constant, we mean that it's same everywhere. But people have been, like, various theories have been put up so as to say that it varies along different line of sights and stuff like that. But again, there's no conclusive evidence of that as such, meaning that it varies along different line of sights or something like that. So yeah, that sort of concludes my answer.
I think these sorts of questions are really great because y'all are coming up with the same questions that scientists are asking about these things, because we really don't know. It's an exciting space to be working in.
Yeah, I've definitely heard it theorized that dark matter, dark energy isn't like a form of energy so much as like an inherent property of space, that space itself must expand. And so the reason space keeps expanding is because it's sort of self-propagating recursively. Who knows? So I call it dark energy. I don't see anything else popping up, but we can give it a minute or two.
I think we'll give it that minute or so, and if we don't see anything, we'll probably call it a night.
Yeah. Very weird watching myself on a 30-second delay.
Oh yeah, it's always strange. All right, it's looking like that might be all we have for tonight. So thank you to everyone who tuned in. Thank you to Bob and Anne, who have been champs. And I hope that you all have a wonderful evening.
Thank you, guys. Bye-bye.
Thanks, everybody. Have a good one.
Good night.
All right, and we are